basically maybe like one class behind. So we're going to be doing analysis of algorithms today. And remember, next class on Wednesday, we do have a quiz. It's on exceptions and analysis of algorithms. So the material we're going to be covering today is going to be stuff that you might see on the quiz on Wednesday. But make sure you look through the chapter, because if there are any points that I might miss or overlook, it's still your responsibility to know what's in the quiz. Okay? And then what we're going to be doing is we're going to jump in after the quiz. We're going to get into abstract data types. We're going to start talking about what is going to cover a good chunk of this rest of the semester. Because we're going to be doing a lot of work with abstract data types up until the end when we get into searching and sorting and that sort of stuff. But a good part of the course is intended to cover Java as it applies to things like lists, stacks, and queues. And those are examples of abstract data types. We're talking about those. So it'd be helpful as well if you are previewing the chapter. Chapter 12 starts talking about that. So it might be helpful if you preview that for the next class as well, so we can jump right in and start covering that information. And again, there's a wealth of information here. If you want to jump ahead in the slides, the data structures, abstract data types is a good one to go to. I'm going to talk a lot about, at least for next class, arrays and linked lists. Because when we start implementing these things called abstract data types, there's two basic ways that we do it. One is through arrays, which you're familiar with. Another one is what is known as linked lists or linked structures. And what we're going to be doing is we're going to be discussing those first so that we understand how we implement these abstract data types, and then we're going to jump into actually the abstract data types themselves. Okay? So any questions for me before we get going as far as analysis of algorithms? No? Excellent. Okay.
Real quick, on the homework, are you going to give us like a little brief intro on some of them, like the analysis of algorithms after today, or kind of get us going?
Yeah, I probably should a little bit. I could, let's see. We'll spend a little bit of time on a class on Wednesday, introducing those that assignments, if you have questions. Yeah. If you have any questions before that, just let me know. Okay? All right. Let's see, what else? Anything else? Thanks for this. Sometimes we get to introduce some things, but we really are kind of packed in there. All right, so let's go ahead and jump in. These are slides. What I did is I updated these slides today, so if you look at these slides before or download them before, they haven't changed a little bit. Mainly, I've just edited them for some content. If I realized earlier today when I had my other class, I need to edit a little bit more, just to keep things consistent. But anyway. That is applicable to this crowd as some of the other crowds that I don't speak to. Anyway, computer science does involve math sometimes, so sometimes it can be kind of complicated. Some of what we're going to talk about today can be construed that way. We're going to try and keep it as simple as possible. Just introduce the concept, but not get too far into it. For those of you who are comp sci majors and are going to be going on to 321 and 421, you can get a lot more of this stuff. You'll be talking a lot more about that. For other folks, it's just to introduce you to the concepts. Because it's important, because if you're going to be implementing software, you want to make sure that you're doing it as efficiently as possible. And especially in business, there's a lot of trade-offs that you have to consider. So in this question right here, Alex, is Alex here today? Alex is not here today. Jeff is not here today. Let's see, Crystal is not here either. Katie's not here. Let's see, Brandon's here. How you doing, Brandon? Good. So what do you think of this question here? So I have this program, this fantastic program, to find out what runs between 2 and 1 billion in 1.3 seconds, or 1.37 seconds. Is that good?
I'd say it's pretty good.
That's good. Who's our math people in here? What do you think, Jesse?
I said it depends, and it would be based on how much processor speed you have. Like if you had a super fast computer and it takes it 1.37 seconds, that's a pretty awful solution. Your program is terrible. But if you're working on a really small machine and it takes it 1.37 seconds to come up with that list,
Yeah.
then it must be a fantastic algorithm. So it depends entirely on the machine you're running it on.
It depends on the machine that you're running. It also depends on the program too, doesn't it? I mean, what if I have another program that can do it in half that time? And then thinking about the problem itself, if anybody knows about, there's a lot of research that goes into this, and it's a really hard problem to try and find the primes between 2 and 1 billion. So if you want to look at it right on the face of it, that's actually not a bad time, but you're absolutely right. And that's the point I'm trying to make here, is that it depends. It depends a lot on the machine you're running on. Is it some supercomputer that, Watson, well, I hate Watson, but anyway, some supercomputer.
IBM.
The reason why I hate Watson is that, okay, so Watson can beat somebody playing chess, right? Do you know why Watson can beat somebody playing chess?
It plays every single iteration.
Because it can look at all the different possibilities. It's a finite world. It's not the world that we live in. If you put Watson up here and told him to navigate from here to there without bumping into anything, he couldn't do it probably, or not very easily. So that I have a problem with it. But anyway, sorry, my personal issues. But the point that I'm trying to make there is that you can have a supercomputer, and maybe this does look good, but maybe I'm running my, I'm running it on an Apple I or something like that, and it's like 30 years old, and it's doing this, so maybe it could still be good. So what we want to be able to do is we don't want to have to worry about the machine that we're running on. We don't want to be concerned about the context of the program, because you can't compare that. It's apples and oranges through, and so what we're trying to do is strip away all of that. And what we're going to be doing is we're going to look at the code itself. And so that's how we're going to determine and look at run times, and that's what we're looking at run times. There's also consideration of space as well. We'll talk a little bit about that, but mainly we're going to look at run times. And so we're looking at efficiency. We analyze them so we can do them better, right? There's always a way that we can improve on things. And if there's a good way of doing it and passing that on to somebody else, that's what we want to do. So how efficient is the program? How much time does it take? That's really important. Time critical systems. If you're on, you have the space shuttle, which they don't have anymore, but in the old days. And you had something that it was, and you needed to make sure that it was checking the sensors all the way around your engines and all that other stuff. And you needed that information like instantaneously. A delay of 1 second could kill people, right? Same thing for like you're a strike fighter, right? You're in the Air Force and you're flying an airplane. You don't want there to be a delay when you're trying to maneuver out of some sort of dogfight, right?
Well, the machine that Enigma that they used to solve that, they only had 24 hours to solve the code before they changed the code.
Yeah.
So they had to figure it out early, otherwise they could figure it out in 2 days, but that didn't matter because the code's already gone.
Yeah, exactly, right, exactly, stuff like that. So time is important. Space is also important as well. Not always, we usually don't tend to talk a lot about space, but it is an important consideration. One of my students earlier today, he mentioned that he was working in a company and they're comparing compression algorithms, right? They have a lot of data and they want to compress it down as small as possible. Well, one compression algorithm got stuff down to like 80% of its original size, which is pretty good. But it took 10 times as long as the other one, which got it down to like 85 or 90%. So they were willing to trade off space for time. They wanted something that was going to run more quickly and they were willing to have it take up more memory. And then the important part that we're talking about is how that changes with the amount of data that we have. What we're talking about when we're doing this analysis is we're talking about with large data sets. And the way we usually refer to that is as the size of the problem asymptotically approaches some large number. In other words, as we get closer and closer to an infinite size, what is the overall behavior going to be? What's the most important terms? What are the most important things that we need to worry about? How is that going to affect us? So this is an example of code, and what we're going to do first is we're going to talk about how we can count the lines in the code. Because again, what we're going to do is we're going to come up with some simple way to be able to come up with a quantification of what it is that this program is doing. And the way we're going to do that is we're going to count. We're going to figure out how much each statement is going to take. Now, if you look at a statement like this where we're just allocating some space for a variable, that doesn't take much time. Even assigning a value doesn't take much time. Now this right here, we're allocating space for a variable, and then we're doing all this math. We're still going to consider each one of these things to be a one count. Now, for those of you who might have a little bit of information about computer architecture and stuff like that, these things right here, especially division and this mod thing, they take up a lot of time. But here's the thing. If we're talking about really large data sets, the amount of time one of those calculations takes is going to be obscure. It's going to go away in the noise. Okay? And so that's how we can get away with just counting that as one statement, this whole thing. This is just an addition, same thing. There's another ugly Boolean expression that might take some time. We're still going to count it as one statement. The only thing we're going to worry about is if, outside of loops, and we're going to talk about those in a second, outside of any kind of loop, the only time we're going to consider it taking more time is when we're allocating large amounts of space. Okay? So for whenever we want to allocate 100 slots for an array, right? We're going to go ahead and count those at 100. Okay? So this is just the way we're going to do this. This is the way this is going to work. There's a lot of things that are not necessarily absolutely correct about this, but this is just a simple way that we're going to count so we can compare our different programs. And then this one right here, again, there's some math going on there, but we're going to still count it as one. So let's look at this problem right here, or this situation right here. So Catherine, if we have this situation, so let's just dissect a little bit more, and maybe do a little bit of counting in our heads here. But before we count the actual statements, just go ahead and look at this real quick. So we're going to set this variable called total to 0. We have an outer for loop. We have an inner for loop. Now, I don't have the braces on here just because there's not a whole lot of space in these slides for me to do that. So this is nested inside of this. And then this is inside of this for loop right here, okay? And so what we're doing is we're adding 2 each time go through, and then we're going to print out the total. So first of all, how many times is that outer for loop going to execute? 13, okay? Travis, where's Travis? Is he here? Travis is not here. Gosh. Miranda. What about the inner for loop? How many times is that going to execute? The inner for loop. We got the outside one, we said what? This is going to be 13 times, right? It's going to go from 0
To 12.
I'm sorry? The next one?
No, the top. Sorry, I interrupted.
The outer one's going to go 13 times. Okay?
Yeah.
What about the inner one?
11.
It's going to go 11 times, okay? Does everybody follow that? Because we start at 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? That's 11 times, right? Because we start at 0 and go all the way up to 10 for I, and that's 11. Does everybody follow that? Because it's important. We're going to have to do that more later. Okay? So this is going to execute 13. This is going to execute 11. How many times is that middle thing going to be executed then? Corbin? Where's Corbin? There you are. How many times? Exactly, right? Does everybody follow that? You multiply 11 by 13. Because this is going to execute 11 times. So this is going to be 0. We're going to execute this 11 times. 1, we're going to execute another 11 times. 2, 11 more times, okay? And so what we're going to end up with is we're going to end up with 11 times 13, which is 143. But is that the total that we're going to have? It's going to be what? It's going to be twice that. So it's going to be actually this, okay? All right?
Yeah.
Does everybody follow that? How we kind of counted those loops? Okay.
Why are we counting them like that?
Now let's look at this code.
2 every time.
So in this case, okay, so Sam, this is a similar sort of situation, right? Except we have these 2 variables, n and m. And all we basically have done here is we've replaced 13 with n, and we've replaced what? 11 with m. And then we're doing this 5 times. So what is going to be the result of this?
See?
So n times m times 5, so c.
Yeah, exactly. So everybody follow that? We're going to execute this outer one n times, and this inner one m times, so that's m times n. And then this is going to be updated 5 each time, so it's going to be 5 times that amount, is what we're going to do. How about for this one? Is Joey here?
Can you clarify something for me?
Yeah, can we go back?
Yeah, you can go back.
Because you're,
So maybe we're saying the same thing, but
Do you want the first one?
are we doing the number of lines or the size?
What we're doing here is we're trying to figure out what total is at this point, okay? We're gonna get to the number, of statements.
So we're not doing counting.
We're not doing the counting yet, we're gonna get there, okay?
So that, I guess that's where I'm getting.
Yeah, I understand. Jesse?
so like on slide 5, you said that a variable a variable assignment and the math that took place
Yes.
after it was one statement.
Right.
So total plus equals 1, or sorry,
It's
plus.
one statement, but the thing is that it's being updated by 5 each time.
So the amount that it's being updated is critical, like how much I'm
We're
adding?
outputting is the total, right, which is the value of that variable. We're not actually counting statements yet, we're gonna get to that in just a
Okay.
second.
I guess
Okay.
that's where I got confused.
We're just looking at the variable value. Yeah, what you want.
Variable value.
So the
I
answer
understand.
is a C?
For this one, it's C, yeah. Yep. Okay.
Okay, great.
And again, we're just looking at the variable value. We're gonna figure out what the result is at the end of this. So, I'm sorry. Go. So Joey, what is the value of result gonna be at the end of this?
I think it would be values.length.
Okay. All right, so what is this representing here? This is the length of our array, right? So it's a size, right? The way that we're going to refer to that in general is going to be n. That's the variable we're going to use for the size of our inputs, okay? This is going to execute that many times. So we're going to say n times, okay? So we'll just say that n is going to be equal to values dot length.
So it'd be n times n. N.
Actually, no, we don't have that. Sorry. So what are we doing in here, in a sense? We're updating this,
And adding it to its index.
whatever that happens to be, right? The value, the actual values that we're adding up. Let's say that C is equal to the largest value, okay?
So it'd be n squared.
In there. Okay? So we're adding C. C is our largest value that we're going to have in this array, right? So we can pretend like we're adding C to it every time, right? So we're going to end up with what? The value of C times n, right? Does everybody follow that? We're going to execute this n times, or the length of our array, and then we're going to add to it the values, the actual values that are in our array. If we say that C is the biggest one in that array, at most, this is the result we're going to get, right? We're going to add C to it. Even though the values might be less than C, as long as we're looking at something that's the greatest, or a bound, an upper bound on this, we can say that this is what results is going to be at most.
Once again, we're just figuring out the result of the operation.
We're just looking at the result of the operation right now, okay? Does everybody follow that? Okay. Yeah, Sam.
So assuming that this is an array of values and saying that C is just a single value in every single index, or C, it's going to be C n times.
Exactly.
And you're saying that this is just the general case that we're not sure what the values are, but
We can't
at
know
most-
that. We can't know what the values are, right? Unless we have some information about our data. We don't.
Okay, so at most it's going to be C times n.
Yeah. In the worst case, they could all be the same values, and they would be the largest values, right? Okay. And we normally say that n is equal to the length. Okay, but that's just something we're going to use. All right. Yeah, Karen.
So wouldn't the total number of statements executed by the method be at most C times n plus 1? Because you said result equal to 0.
Well, again, what we're doing is we're looking at two different things. So we're looking at, this is what results at most is going to be.
Oh,
Okay.
okay.
Right. Okay. And now we're going to start. Now we're going to go back because I wanted you to get used to that whole counting of the for loops. That's what we're doing. That's the whole idea. Because we're going to need to count for loops
And the
before we
reason-
start counting these things.
The reason that you're saying C is the largest value, is that coming up later? Why you care that's the largest?
Well, because, okay, so let's say that you're worried about how